Today we're going to look at a new method of proof called proof by contradiction. And to prove something by contradiction, we assume that the opposite of it is true, and then we disprove that statement, meaning that the original statement must be true. Let's look at an example, and the first example is that to prove that n squared is even implies that n must be even. So we're going to assume the opposite. So assume if n squared is even, then n must be odd. And if n is odd, then we can write n as 2p plus 1 for some integer p. 2p would be even, so 2p plus 1 would be odd. So if n is 2p plus 1, then n squared is 2p plus 1 squared. And expanding 2p plus 1 times 2p plus 1 gives us 4p squared plus 4p plus 1. We can see 4p squared plus 4p is even because it's two lots of 2p squared plus 2p. So 4p squared plus 4p plus 1 must be odd. So let's just write that down. So two lots of 2p squared plus 2p is even. So n squared is odd. And this is where we get our contradiction. So we're going to point that out. That's our contradiction. It contradicts our assumption that n squared is even. Therefore, since our assumption is wrong, then the original statement must be true. Remember to mark the end of your proof with a box or QED. So those are your steps. Assume the opposite, work with that, come up with some form of contradiction of your assumption, which means your assumption was wrong and the original statement is true. Now we're going to use what we've just proven here, that if n squared is even, then n must be even, to help us prove by contradiction that root 2 is an irrational number. So our assumption is the opposite of this, so we're going to assume root 2 is rational, and if it's rational, it can be written as a fraction. That's what a rational number is. So let's say it can be written as p over q, and let's assume that that's in its simplest form. So that would mean p and q are integers, and if it's in its simplest form, then they must have no common factors other than 1, which means they are co-prime. So that would mean they are co-prime. Let's just make a note of what that means. No common factors other than 1. So if root 2 can be written as p over q, we can make that look a little bit nicer by squaring both sides. 2 must be p squared over q squared. And if I times both sides by q squared, that tells me 2q squared equals p squared. Well, if p squared is 2q squared, that means that p squared is even. And using what we proved in example 1, if p squared is even, then p must be even. And if it's even, then it can be written as 2 times something. Let's say p is 2 times m, where m is an integer. So if I replace p with 2m, so 2q squared is 2m squared, timesing out my brackets, that means 2q squared is 4m squared, and halving that tells me q squared is 2m squared. Well, this means that q squared is even, because it's 2 lots of something. And using example 1, if q squared is even, then q is even. So q is 2 times something. Let's make it 2 times n for some integer n. Therefore, root 2 is p over q. Now that can be written as 2m over 2n, but that would mean that p and q are no longer co-prime. They now have a common factor of 2. So this contradicts the assumption that p and q are co-prime. Since they have a common factor of 2. So if they are not co-prime, then there is no way of writing root 2 as a fraction in its simplest form. So there's no way of writing root 2 as a fraction, so therefore root 2 must be irrational. And this is a really common exam question to get you to prove that root 2 is irrational, or maybe root 3 is irrational, or root 5 is irrational, and you're going to use the same logic with those. Right, let's look at one final example of proof by induction. Again, a really common example, and this is to prove that there are infinitely many prime numbers. So our assumption is the opposite of that. So we're going to assume there are finite primes, and let's call them P1, P2, all the way up to Pn, where n is the last prime numbers. And then let's consider the number that we get if we times all of those together. If I times all of those prime numbers together and then add 1, I'm going to get a new number. And because every single integer can be written as a product of primes, then there is a prime number that can divide into p. There's a lot of writing in this work, since all integers can be written as a product of primes, which we know because we can do prime factor decomposition of every number, and if it's a prime number then your prime factor decomposition just gives you that number itself. So we must have a prime factor, let's call it P, so little p is a factor of this big P, which is all the primes multiplied together with 1 added on to it. Now that must be a factor of the product of all of the primes, because P is a prime number, so it must be a factor of all of the primes multiplied together. So it's a factor of big P and of the product of the primes. So it must be a factor of those two things taken away. So for example, if you have a multiple of 3, take away a multiple of 3, you will get a multiple of 3 as your answer. If you've got a multiple of 10, take away a multiple of 10, you will get a multiple of 10 as your answer. If we've got a multiple of our prime number little p, take away a multiple of our prime number little p, then we will get a multiple of little p. But p minus the product of primes equals 1. And you can't have a factor of 1 other than the number 1 itself. And because p is a prime number, little p is a prime number, little p cannot be 1. So this is a contradiction, since little p is not 1, so cannot be a factor of 1. So, assuming that there were finite prime numbers led us to come up with a prime factor of this number here, which is the product of primes plus 1, and that prime factor ended up having to be a factor of 1, but there are no prime factors of 1 because the only factor of 1 is 1 itself, and that is not prime. So that's led us to believe that this assumption must be false. Therefore, there must be infinite primes. So our original assumption is false. And there are infinite primes. Now this doesn't use any logic beyond sort of year 7 maths really, but it's a really difficult concept to get your head around at first. So let's run through it one more time. So because we want to prove that there are infinitely many primes, we make the opposite assumption and we assume that there are a finite number of prime numbers, and we're going to call the prime numbers the first prime number P1, the second prime number P2, all the way up to the last prime number Pn. And we're going to consider what happens if we multiply all of those prime numbers together and add 1. And we're going to call that value big P. Now, because all numbers can be written as a product of primes, then this big P must have a prime factor, and we call that prime factor little p. And because that number is a prime number, it must be a factor of the product of primes. So it's a factor of big P, and it's a factor of the product of primes. So it must be a factor of big P minus the product of primes, which happens to be the number 1. So we've got a number which is a prime factor of the number 1, which is a contradiction because there is no prime factor of the number 1, and that whole contradiction means our assumption was false. Okay, I'm going to set you the questions to do on this from the worksheet, and I'm going to ask you to submit this to me to be marked, please.